motor units, we're going to go back to that idea. Hopefully you had a chance to review that horizontal slice through the muscle fiber, rather through the muscle. So a motor unit is a motor neuron, a motor nerve, and all the muscle fibers that attach to it. So this diagram is two motor units, right? And there are several important things that we want to understand about the motor unit, okay? The first one is that a motor unit is either slow or fast fatigue resistant, FFR, or fast fatigable. Okay, so they're going to be one of three. And what they are relates to the kind of muscle fiber that they are synapsing with. So if it's a slow motor unit, they are synapsing with type 1 muscle fibers. If it's a fast fatigue resistant, then they are fast fatigue resistant, then they are synapsing with our type 2As, because they're the ones that have some capacity for using oxygen. So although they do fatigue quite quickly, they're better than our type 2X, all right? And our fast fatigable is our type 2X fiber, or it could be type 2As if they've undergone some change with training, if the type 2Xs have undergone some change with training to type 2As. Right, so we talked about that adaptation earlier in the week and last week. Right? So the motor unit is one motor nerve plus the muscle fibers, the muscle cells, not the muscle, the actual fibers, right? The muscle cells that nerve synapses with. The number of muscle fibers that it synapses with depends upon the amount of control that's required that nerve is in charge of. All right? So the finer the control, so in the eye, for example, the nerve will only synapse with between 5 to 10 muscle fibers to move your eye around, because it's got to have very tiny, clear, distinct control over the eye. All right? When we look at a motor neuron that's synapsing in the calf, then that one motor unit may contain 1,000 muscle fibers, because I don't need fine, clean control over the calf. I want gross control. I want the whole calf, as much of the calf to contract as possible. On average, it's somewhere around 100 to 150, right? But just the numbers are less important than the concept that if the motor unit is controlling fine movement, then there's less fibers within the unit than there are if it's controlling a gross type movement. Right? So if we say, let's say that this is a slow, right? Then this is a type 1, this is a type 1, this is a type 1. Right? If this is an FFR, then this is a type 2A, this is a type 2A, this is a type 2A, and this is a type 2A. Does that make sense? And I think it helps when you think back to that horizontal section with the different stained, different color stains on the muscle fibers, because that gives you the picture of the fact that I can have slow and fast muscle fibers all in one bundle or in one muscle, right? One muscle isn't either slow or fast. One muscle is made up of many fibers and motor units, some of which are slow, some of which are fast. Right? The other day, we're kind of working back up the chain. We did the muscles, now we're doing the nerves. Now we want to look at how does the signal travel down the nerve and travel across the muscle. All right, so we're going to look at the actual transmission of the electrical signal. And I suspect you did this in A&P, but it may have been A, complicated, and B, quick. So I'm going to take it as slow as I can. Give me a yell if you need me to repeat something, all right? All right, so the impulse, the signal, the technical term for the impulse or the signal is the action potential. And that signal is what stimulates the sarcoplasmic reticulum to release the calcium so that we see muscle contraction. All right, so what we want to know is how does the signal get from the brain down the spinal column and out along the motor neuron to the muscle. Okay. So when there is not an impulse or a signal being transmitted, then the membrane of the nerve or the membrane of the muscle is said to be at rest. Right? When we look at resting membrane potential in our muscles and our motor neurons, it's about minus 70 millivolts. All right? So this is my membrane. So it can be the outside of the nerve, or it could be the sarcolemma of the muscle. And what we're looking at is the fact that on either side of the membrane, we have charged ions. All right? And so we're looking at the summative effect of these charged ions across the membrane. So when it's at rest, we say that resting membrane potential is minus 70 millivolts. So we measure it just the same way we measure electricity in a wall socket. Right? That means that the difference between the charge on one side and the charge on the other side is minus 70. So if I add up all the numbers, all the charges on one side, and I add up all the charges on the other side, I've got a difference of minus 70 when there's nothing going on. Right? So for a signal to travel along, then there has to be a change in this potential. All right? And we have to reach what we call threshold in order for the membrane to depolarize and for the signal to be able to travel along. Right? So when we look at it here, we have, let me make sure I get this around the right way because I always get it around the wrong way. On the inside, we have lots of potassium and a little bit of sodium. And on the outside, we have lots of sodium and not very much potassium. Okay? So what we want to do is change this minus 70. Okay? So when we depolarize, what happens is that it opens a channel, a sodium gate, and it allows sodium to cross into the cell. Right? So as soon as I start getting these positives floating over, it changes this number. Right? And then, at some point, in order to receive another signal, the membrane has to go back to rest. So it can only take one signal at a time. Okay? So for it to go back to rest, it has to open potassium channels and let the potassium leave the cell. And it shuts the sodium one at the same time so that no more sodium can come across. Very, very quick, all right? If you imagine that in order to move my arm up and down, how many signals had to come from my brain in order to do that? And every signal has to go back to rest before the next signal can come along, right? So the amount of time this takes is minimal, okay? Just a few milliseconds. So this is a much better drawing of the sodium and potassium gates, channels, gates, whatever picture helps you the most. So here is depolarization. So the sodium channel has opened up, and sodium, they've drawn it the other way around to me. This is the outside and this is the inside. So sodium can come through into the cell, change the potential on the membrane. That allows the signal to move along. And then when the signal has to stop, we've got to open our sodium, close the sodium, open the potassium, and move potassium out to regain our minus 70. Okay? And I really like this graph for this. I think it helps a lot. Because here is my resting, this bottom dotted line is my minus 70-ish. It's a little bit under here, it's about 65, but, right? And here is my time in milliseconds. Okay? So I go from rest all the way up to 35, 40 millivolts in under 1 millisecond. And then and that's that. Right? So this piece is this, depolarizing. And then I have to repolarize, so I have to bring it back down. So this piece is this. Okay? I have to bring it back down. What happens is it actually drops a little too low and then comes back to rest. So we overdo it a little bit and then bring it back to rest. And that whole cycle took 3 milliseconds. Okay? Now, the other thing that I quite like about this picture is this other dotted line, the threshold. If I don't have enough sodium crossover here for this membrane to change to this point, this doesn't happen. Right? It would just go back and wait for the next signal. So the signal, the impulse, has to be strong enough to make sure that we go past threshold for the action potential to happen.
It explains it really well, right underneath the picture.
Mm-hmm.
It explains each point really well.
Yeah. So one of the interesting things about these pumps, these channels, is that they use almost 50% of the ATP that we create when we're trying to see muscle contraction. So then if we think back to our animation of the muscle contraction, and we said we had to have ATP there for the myosin head to circle around. So I need ATP for the myosin head for the actual contraction to occur, but I also need piles of ATP in order to get the signal to the muscle fiber for contraction. When we're trying to restore resting membrane potential, we move 3 sodiums out and 2 potassiums in. That's the wrong way around. So our signal goes from electrical in the nerve, has to get across the synapse. Electricity can't cross a gap, so we have to have a chemical transmitter in the synapse, which we'll come back to, and then it turns back into electricity when it hits the sarcolemma to run across the surface and down the T-tubule and stimulate the sarcoplasmic reticulum. Right? The chemical that floats across the synapse, when we're looking at the neuromuscular junction, that chemical is ACH, acetylcholine. ACH is excitatory, so it stimulates another action potential to run across the surface of the muscle. But in some instances, when you look at the chemical at the synapse, it can be inhibitory. So when we look back to that inhibitory interneuron that we talked about, that chemical, instead of stimulating the action potential, blocks the receptor site so that an action potential can't be initiated. So it's a bit sneaky. Right? It'll make more sense in a minute, hopefully. Let's see what we have. Okay. All right. So even though that is really quick, 3 milliseconds for that action potential to occur and for the membrane to depolarize, action potential and repolarize. Imagine how long it would take for a piece of information to leave your motor cortex and travel all the way down to your foot, right? It would take way too long for you to react to a ball that you have to kick, okay? So there's a mechanism in place that allows the action potential to move much more quickly down the nerve. And that is the myelin sheath, right? The myelin sheath is a substance made up of lipid, so it's kind of fatty, and it wraps around the axon of the nerve. So a nerve, particularly motor nerves, that have this high level of myelination are able to conduct impulses much more quickly. They don't have to wait for the action potential to kind of move piece by piece down the down the line of the axon. They're able to jump entire pieces of the nerve. And hopefully I have a picture. Oh, no, I may have to draw you that. Let's see. So we have a motor nerve, right? And here's my muscle. Okay. So we receive a signal in. If enough signal comes in to initiate an action potential at the cell body, then the action potential will travel down the axon to the nerve. But we want it to travel quicker. So we wrap these pieces of fatty tissue around the axon. And now what happens is that the impulse comes down here, jumps that piece, comes down here, jumps that piece, comes down here, jumps that piece. All right, it's called saltatory conduction. And by jumping these big pieces, that speeds it up a lot, yes.
When someone has MS, they don't have,
It's,
to walk.
it degenerates, so it doesn't do the job. And so then what happens is then the signal has to travel down a lot more of the axon so that the signal gets slowed down. And so their movements become uncoordinated because these signals aren't all arriving at the same time. The little gap where the jump is called the node of Ranvier. Right? And it can increase the speed of conduction by up to 150 times over a nerve that does not have myelin around it. All right? So it considerably speeds up the transmission of the signal from the brain. Also, bearing in mind that every depolarization, repolarization uses a pile of ATP, it saves a lot of energy by doing this jumping because it doesn't have to use ATP to get along that part of the nerve. Right, so it does two good things. Gets the signal there quicker and conserves ATP. So how do we control which motor units are turning on and off? All right. What kind of factors play a role in when I turn them on and off and why? All right. So we have a principle called the size principle. And the size principle says that motor units are recruited from the smallest to the largest, based upon the size of the neuron. All right? So how big is the cell body? And that allows me to regulate the number of motor units that are turned on and control the amount of force that is being initiated. So we said before that we have a sequence type 1s to type 2a to type 2x. Right? Type 1s have the smallest cell body. So we turn them on first, generally. And then if we need a bit more force, we turn on our type 2As. And then if we need even more force, we turn on our type 2Xs. Right? So if you imagine that you've packed up a large box full of books, right? And you go to pick up that box and it doesn't move, and then you have to apply a bit more force, and then you have to apply a bit more force in order to get the box up off the floor. Okay? Initially you turn on type 1s, then you add in your type 2As with your type 1s, and then you add in your type 2X with the other two in order to get the box up off the floor. Type 2 muscle fibers have much more capacity for hypertrophy than type 1s. So they're able to get much bigger than a type 1. All right, so when we do a muscle size type resistance program, we're targeting those type 2s to try to make them bigger so that our muscles get bigger. Okay? But I can think of that another way, all right? What that gives me is an explanation for why when I go jogging, I don't develop great big muscles, right? So if I look at a marathon runner has long, lean muscles, relatively small muscles, even though they're very strong. They're not big, bulging muscles. Because a marathon runner uses predominantly their type 1 muscle fibers. And those do not hypertrophy very much. They will get bigger, but they don't have the kind of capacity that a type 2 fiber has. It's also why if we do a weightlifting program where we do lots of reps with light weight, we don't get great big muscles. Okay? If I look at a sprinter, 100-meter sprinters have big legs, right? Big, round quads and hamstrings. Because they're using predominantly their type 2s. Okay. So the size principle works in general, but there are times, particularly in sport, when the size principle would really not help us very much at all. Right? If I'm a sprinter and I'm in the blocks and the gun goes off and I have to initiate first my type 1s and then my type 2As and then my type X, everybody else is going to be at the finish line when I'm 3 strides off my block. Right? So under certain circumstances, we can override the size principle. And this is another form of adaptation that occurs with training. The more I train these sprint starts, jumping into the pool if I'm a swimmer, okay, then the better I get at overriding the size principle and jumping straight to my type 2X. Which if I want to drive out of the blocks as fast as possible, I need those. Right? So, as I said, under certain circumstances, we can bypass the size principle and use the most powerful muscle fiber that we have. When we look at sports situations, that's a kind of training adaptation. The more I work my starts, the faster they get, right? But it also can happen under circumstances where you or someone you love is in danger, right? So you're suddenly able to generate this massive amount of force to lift a car up off a child, right? Or something like that, right? Or climb a tree. Okay? So under situations of danger, we can override the size principle and use our most powerful muscle fibers to help us out of the danger. Right? When we look at turning these motor units on, I mentioned the term threshold already for the action potential. So this threshold is a really important idea because if I don't reach threshold, the motor unit doesn't turn on and or the stimulus will not be transmitted, all right? If we reach threshold, so in this case, if I reach threshold within the cell body, actually it happens at the hillock, which is right in between the cell body and the axon. The hillock adds up all the impulses that are coming into that cell body. If it reaches threshold, the action potential goes, and every motor fiber that is attached to that unit will turn on and contract. Right? So we have the all or none law. Right? Either all the muscle fibers in the motor unit contract or none of them contract. There's no halfway house, and they don't only slightly contract, they contract. So whether I want a powerful contraction or a gentle contraction doesn't come from I only turn the muscle fibers on a little bit, it's which motor unit did I turn on. Because there's tons of them in the muscle, right? If I only want a very gentle little movement, I don't turn on type 2Xs. I turn on type 1s. Right? So the benefits here are quite manifold because we don't want to waste energy turning on type 2Xs if we don't need to. So the size principle and this all or none law allows us to recruit the easiest motor units to turn on, type 1, because they're the smallest. So they need the least amount of stimulation to turn them on, right? And it just so happens then that the easiest to turn on also happen to be the most fatigue resistant. So I turn on the muscle fibers that aren't likely to get tired very quickly. Right? So for daily living activities, when I don't need lots of power, I turn on nice, slow motor units. I use my type 1 fibers. They don't get tired very easily, so unfortunately I'm able to push the vacuum around the entire house. I can't plead that I got worn out after half the living room, right? Because I'm not using these, I'm using these, so I just have to keep going. Right? Okay? So, by using the size principle, it delays fatigue, right? It turns on the smallest, least energy sucking motor units and puts off fatigue. And then if I need more power, because I've got to carry the vacuum up the stairs, then I can turn on some type 2As to help out. So if I don't need a lot of force, I'm going to turn on my slow motor units. Then if I need a little bit more force, I have to add in my FFRs. And then if I need even more force or power to achieve the goal of the task, then I have to add in the FFs. So that's the typical pattern of recruitment, unless we override it and go straight here through training or because of data. So what adaptations do we see? We talked about adaptations in the skeletal muscle system to training. What happens in the neural system, in the nervous system, when we do skill training or strength training? Right? So if we look at strength and power training, then what happens is that initially we see that the amount of contraction increases for a given stimulus that's being sent by the central nervous system. So that happens because of motor unit recruitment. We turn on more motor units and we speed up how quickly those motor units can react, right? The ability that they have to alter the action potential generation, right? How quickly can they initiate that action potential improves with training, right? So then that gives us the possibility of improved activation of the muscle, and probably more effectively is the recruitment pattern. Which motor units do we turn on at any one time? So it's really interesting when we look at an early training plan, strength training plan, all right? Because if I take someone who is low active or sedentary, or someone who hasn't been doing any kind of resistance strength work, and I put them onto a consistent strength plan 2 or 3 times a week, right? Then what we see over the course of just the first week, the first couple of weeks, is a significant improvement in their strength, right? Even if they've just done 3 training sessions in week 1, when you test them in week 2, they'll be stronger than they were in week 1, right? Did their muscles get bigger in 1 week? Takes ages. Any of you have ever tried to put on muscle mass? No, it takes ages to grow muscle, right? And yet, they got stronger, right? And that continues for some time, okay? So the blue line here is strength. The orange line is neural changes, and the green line is hypertrophy of the muscle tissue. Right? So we don't see a lot of hypertrophy when we get this great big initial increase in strength, but we do get significant changes within the neuromuscular interaction. Right? So it's not until later on, now my improvements in strength are more down to the fact that my muscles are getting bigger. And if they're bigger, they can make more myosin-actin cross bridges, and they can generate more force, ergo I'm stronger. Right? So all that initial change in strength is not down to the muscles, it's down to the changes that occur within the nervous system. And when we see declines in strength because someone takes a week off or 2 weeks off, the decline in strength is not because their muscles suddenly shrank. Because as hard as it is to put the muscle mass on, when you quit training, that muscle mass doesn't go away for a year, 2 years. It takes a long time for muscle mass to disappear. But the strength disappears very quickly because of the decrease in neural drive that occurs when you stop training. Right? It's very cool. They also think there's some remodeling that goes on at the neuromuscular junction, so that maybe the neuromuscular junction gets a little larger, and that the amount of acetylcholine that floods across the junction increases, the number of receptor sites for that acetylcholine increases, and so we see remodeling here, as well as the changes from the central nervous system. Cool stuff. How much time have I got? Thanks, not very much time. Okay. Quick point. If I'm doing strength power work, and I want more power, more strength, then it's logical that I need to turn on more motor units. I have to make more muscle fibers contract at the same time. Do you agree? Anybody following me? All good, right? So, with training, we see more synchronization of motor unit firing to generate more strength and more power. If, however, I'm doing endurance training, we see a different picture, okay? Because now what we want is that muscle to be able to keep contracting for 3 or 4 hours without stopping. So I don't want to turn on all my type 1 fibers at the same time, because I need them all to be able to keep going for a long time. So what we see with training is a development of asynchronous recruitment. So the brain gets better at turning on motor unit 1, part 1. And then it turns on motor unit 1, part 2. And then it turns on motor unit 1, part 3. So it takes turns within the muscle at turning on the type 1 fibers, which means that the type 1 fiber that worked first, even though it's fatigue resistant, gets to have a rest while another type 1 fiber does the same job, and then it gets turned back on again. Right? So strength training, we see increased synchronization, more muscle fibers contracting at the same time. And with endurance training, we see asynchronous recruitment of the motor units, so that we turn on some motor units and we give others a rest, but that means we can keep going for hours and hours and hours and hours, and that muscle does not fatigue. Bless you. And then, as I said, at the neuromuscular junction, increased number of vesicles in the axon. So that means more ACH is available. Floods across the junction. Increased number of receptors on the sarcolemma allows us to reach threshold quicker and initiate the action potential more quickly. So the only slide that I haven't finished, make sure please that you take a look at it before Monday, is the practical applications. They're kind of obvious, right? What kind of training I do dictates the adaptation that I see. Okay. Monday will be the review session on Chapter 4 and Chapter 5. Wednesday will be the exam. If anybody cannot make Wednesday, I need to know. And Friday, I want you to seriously take time to work on your physical activity logs, because I have not had very many questions about those, and they are due the following Monday. So I'm a little worried that people are not doing them. Yes?